In this operations management video, we're going to talk about process capability. Specifications are a range of acceptable values established by the customer. In other words, they have absolutely nothing to do with your equipment or your processes. They're simply what the customer wants. Process variation is the natural or inherent variation in a process. That's your process. Process capability is the inherent variability of the process output relative to the variation allowed by the design specifications. In other words, how well your process matches up with the customer specifications. Specifications from the customer are often expressed as tolerances. They're generally expressed as a plus or minus value. For example, you want a package filled up to 16 ounces plus or minus half an ounce. Or you want holes drilled 1 inch plus or minus 1/100th of an inch. Both of these examples I've given you are symmetric tolerances, but that doesn't have to be the case. It could be 0.99 inch to 1.03 inch. Tolerances have absolutely nothing to do with the control charts we're going to talk about in another video. Control charts are a way of monitoring your process over time. Tolerances or specifications are simply what the customer wants you to provide. Imagine you're a company that makes bolts. You might sell bolts to Home Depot. You might sell bolts to Lockheed. As you might imagine, those two customers would have very different tolerances. You might be perfectly and completely capable of making acceptable bolts for Home Depot, and yet be completely incapable of making bolts for Lockheed. There's nothing wrong with that. You look for customers that match your process. If your process can't produce bolts that are acceptable to Lockheed, you don't go after Lockheed as a customer. In all of these next couple of examples, I'm going to show process variation as a normal distribution. When the customer specifications match your normal distribution, then you have a process that is capable. In the case shown on the screen right now, I would say it's barely capable. When your process variation is much less than the customer specifications, then you can produce products that are well within specifications. In other words, you're very capable. The greater the distance between the normal distribution and the specifications, the more capable you are. And this is really the foundation of Six Sigma, which we'll talk about later. When the variability of your process exceeds the customer specifications, as it does with the example on the screen right now, then you're not capable. You're not capable of meeting this customer specifications. You might well be able to meet many other customer specifications. Does this mean you should update your process? No. If you're making bolts for Home Depot, it may not make a lot of sense for you to update your process to make bolts for Lockheed. After all, the kind of bolts that Lockheed's want are a lot more expensive than the kind of bolts that Home Depot wants. If you spend all of that money to make your process capable of supporting Lockheed, your bolts may be too expensive for Home Depot. We're going to talk about two approaches to measuring process capability: the process capability ratio, CP, and the process capability index, CPK. If the process is centered, that is, if you're producing the mean that matches your customer's mean, then CP is all you need. If your process is not centered on the customer specifications, then you need to use the process capability index, or CPK. Realistically, in the real world, CPK is always a better measure because you cannot always be sure that your mean matches the process mean. So just use CPK and you don't have to worry about it. A value for CP or CPK of 1.00 means that you are capable, barely capable. That's where the customer specifications exactly line up with the endpoints of the normal distribution, or technically the plus and minus 3 standard deviation units of the normal distribution. A value less than 1.00 means you're not capable. The more the value exceeds 1.00, the more capable you are. We'd really like to see it about 1.4 for most customers. If it's 2.00, then that's essentially Six Sigma. The formula for the process capability ratio and process capability index are shown on the screen. And remember, I have video tutorials on how to work all these problems, and I'll tell you more about those in a moment. For these formulas, UTL is the upper tolerance limit, and LTL is the lower tolerance limit. Those are the values from your customer. They're just expressed as numbers instead of plus or minus because they don't have to be symmetric. The process capability ratio is simply a ratio of the width of the tolerances from the customer divided by the 3 sigma width of the process, that is, the plus and minus 3 sigma. That's why you divide by 6 sigma. It has nothing to do with actual 6 sigma. For the process capability index, you compute two numbers. Now, a lot of students, when they're working this problem, compute those two numbers and then think that's the end of it. That's not the case. Once you compute the two numbers, you take the smaller of the two. One number is the upper tolerance limit minus the mean divided by 3 sigma. The other is the mean minus the lower tolerance limit divided by 3 sigma. And again, you take the smaller of the two. My students can access the video tutorials for these problems using the content menu in D2L. YouTube viewers can access the video tutorials on my MOOC on udemy.com. I have a long and short version of the URL posted on the screen, and I will post this URL in the description. There are some limitations on both the capability ratio and the capability index. The first one is that the process may not be stable. In other words, your production mean might be drifting. This won't be picked up by either measure, although hopefully it'll be picked up by a control chart. Second, the process may not be normally distributed. That's an assumption of both the process capability index and the process capability ratio. The further your process is from being normally distributed, the more misleading the values can be. The third is the process not being centered, but using the process capability ratio, CP. That's always a risk, and that's why it's always better just to use CPK, the process capability index. So if you don't like your value, how do you improve it? Well, we've already discussed that you might not want to improve it, but let's say you do. There are a number of things you can do to reduce variation. You can never eliminate it. There's absolutely no way to eliminate it, but you can reduce it. One thing you can do is simplify the process. The simpler the process is, the less variation there's going to be. Another thing you can do is standardize. That is, use the same thing over a lot of different processes. That doesn't inherently improve process capability, but it does give your workers more practice, and that improves process capability. You can include mistake proofing in your process, assuming that's possible. Those mistakes increase variation and lower your capability. You can upgrade to better equipment, which is certainly what you'd have to do if you're going to switch from making bolts from Home Depot to making bolts for Lockheed. That's expensive. You can also automate. Robots have less variation than humans. They have variation. It doesn't eliminate the variation, but they have less of it. Again, that's expensive. Let's briefly look at 3 sigma and 6 sigma quality. The process capability index and the process capability ratio are based on 3 sigma. When your process plus and minus 3 standard deviation units, in other words 3 sigma, exactly matches the customer specifications, you get a process capability index and ratio of 1.00. When you have to go more than 3 standard deviation units out from your process in order to meet the customer's tolerances, then your process capability index and ratio are greater than 1.00. When you have to go out plus 6 standard deviation units to the right or minus 6 standard deviation units to the left before you reach the customer tolerances, then your process capability index and ratio will be 2.00. That's essentially 6 sigma. In other words, you have to go plus or minus 6 standard deviation units before you exceed customer tolerances. And that, as I said, yields a process capability index and ratio of 2.00. There's more to it than that, but that's kind of a rough idea of it. What that really means, since the probability of exceeding 6 standard deviation units in a normal distribution is so low, you're almost never going to exceed the customer tolerances due to random variation. Now let's briefly talk about the Taguchi cost function. Standard quality control says that as long as it's within the customer tolerances, it's completely acceptable to the customer. So let's say, just for example, that they want a hole drill that's 1 inch. They're willing to tolerate a hole that's as small as 0.9 inch or as large as 1.1 inch. So it's 1 inch plus or minus 1/10 of an inch. Traditional quality control says that a hole that's drilled to 0.9000 inch is just as valuable as one that's drilled at 1.00 inch, which is just as valuable as one drilled at 1.100 inch. That's probably not true. The customer would probably value it more if it's closer to 1 inch. That is what Taguchi thought. That's what his cost function is based on. His idea was that that hole was the most valuable to the customer at 1.00 inch. And as you moved away from 1 inch in either direction, even if you were in tolerances, it became less valuable to the customer. Additionally, traditional quality control says once you pass a tolerance, either an upper or lower one, it becomes of no value to the customer. In other words, a hole that is drilled to 1.100001 inch has no value, and a hole that's drilled to 0.899999 has no value. That's probably not true either. So really, according to Taguchi, it has its most value at the center, and the value goes down as you move away from the center, but there may still be some value once you pass the tolerances. The diagram on the screen shows this visually. The y-axis is cost, so the higher you go up the y-axis, the higher the cost. According to traditional quality control, anything between the tolerances has the same cost. That's the vertical lines. The curved lines are the Taguchi cost function. The further away you move from the mean, the higher the cost to the customer. In other words, the lower the value to the customer. But it's not digital. It's not when you cross the line, the upper or lower tolerance, it becomes 0. If you enjoyed this video, please click like and consider subscribing to this channel.